So I hope you're doing well today. I want to talk about the product rule and the quotient rule for derivatives in this video, or these sets of videos. And so we've got our first theorem right here, right off the bat. F is a differentiable function and G is a differentiable function. So remember what that means, that you are allowed to take the derivative of these functions. Notice it says when you take the derivative with respect to x of these two functions multiplied together, hence a product, then, watch this, it's the first times the derivative of the second one. So you just leave the first function alone times the derivative of the second function plus, then you write the second function and leave it alone times the derivative of the first function. Now here's what doesn't matter. The order you write this down in honestly doesn't matter. What you're doing is you're holding one constant to its original function times the derivative of the other, and then adding, then hold the next one constant times the derivative of the other. So first times the derivative of the second, plus the second times the derivative of the first is the way I say this all the time. Now, where does that come from? Well, I need to show you the proof, so this time I'm not going to write it out for you so you can read it a little bit better, so here we go. Step one, we begin with the definition of the derivative. That's what we always begin with, right? You remember the definition of a derivative. Let me write it down for you just in case you don't. Remember the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. Now what is our function this time? Well, our function is f of x times g of x. So when I plug that in, it looks like this. Right? So I have f of x plus delta x times g of x plus delta x minus my original function f of x times g of x over delta x. Now what we do next is a little weird. Okay, we got a weird trick. We're going to add and subtract a weird factor, f of x plus delta x times g of x. Okay, so I say a weird factor, it's really a term. I'm going to add it and subtract it. Now that's allowed, right? I'm really not changing the value of my limit. I'm just subtracting, see? I'm just subtracting this new term, f of x plus delta x, g of x, and adding the same thing. So it's like adding 0. And notice the rest of it is exactly what we have for our definition of the derivative. Now, why would I do such a thing? So I can group these together and factor, of course, right? Now look what happens when I do that. So it says now you will split your limit using the sum difference formula for limits. So look, see if this makes sense. All right, so what I did is split it up. I put the d of x underneath each of these two separate terms. So I have f of x plus delta x times g of x plus delta x minus f of x plus delta x g of x over delta x here. And then the same thing with these second two terms in the numerator over delta x here. Why am I allowed to do that? First, I split the fractions. I really did two things in this one step. It's kind of a space saver. But I have two separate fractions that I split up. And then on top of that, I split the limits up. You know, we have a sum difference rule for limit. And so if you want to split two limits up, you're totally allowed to do that. Now, the next thing we want to do is that factoring I mentioned a minute ago. Okay? So all I did, y'all, is give myself more room. So we were in the same place we were before. This is the same exact line. We want to factor the greatest common factor. So when you look at that line, notice that both of these have an f of x plus delta x. I'm going to factor that out. Whereas your second limit has a common g of x that we can factor out. So that's what I'm going to do. So here we go. There's that f of x plus delta x that I highlighted. And notice the g of x plus delta x minus g of x is here. And then the g of x, that's what I highlighted. And then we still have f of x plus delta x minus f of x over delta x. Okay? So really, so far, we added and subtracted this strange term, but it was really 0. We split it up into two separate limits. We factored the greatest common factor. And here's what I want you to think about. It's time to evaluate these limits, okay? So let's look at this limit on the left. If I have the limit as delta x goes to 0 of f of x plus delta x, I'm allowed, because f of x, remember, is differentiable. It's over here in the setup for the product rule. F of x is differentiable. Therefore, it's continuous, which means I'm allowed to plug 0 right into this delta x. So that's going to be 0 right there. Okay? Actually, let's don't even do that yet. Let's back up. And here's why. I'm trying to erase this. So once again, my computer's trying to freak out on me. Thinks there's too much information. But anyway, let's don't take those limits yet. You know why? Because I have a product here, and I can split this up into 2 separate limits. And that's what I want to do now before I take those limits. So look at this next line. Use the product rule of limits to split each. There I go. So look, I've got the limit of the first one now separate than the limit of the next one, plus, that plus is so hard to see right there, the limit of g of x times the limit of that function. Now I'm ready to take the limit, okay? So because f of x is a continuous function, I'm allowed to substitute 0 in directly into delta x. Now what is this? Does that look familiar to you? The limit is delta x goes to 0 of g of x plus delta x minus g of x over delta x. Doesn't that look just like the derivative? What's that the derivative of? Well, that's the derivative of g of x, right? So when I plug 0 in here, that's just going to give me f of x times, and this is the derivative of g of x, so that's g prime of x, plus we've got the limit is delta x goes to 0 of g of x. That's just a constant. There's nowhere to substitute in delta x, so that's plus g of x times, now that ought to look familiar as well, right? That's the derivative of f of x, so that's times f prime of x. I'm so over this computer right now. I apologize. It's back. There we go. Okay? So that's it. Now I'm going to show you it typed up. And there it is typed up instead. We evaluated the limits, and at the end of this proof I make that point again that since f of x is differentiable, that means it's continuous, and that means I'm allowed to plug in the delta x, substitute 0 in for delta x. You couldn't do that if you didn't know you had a continuous function because it might be undefined, right? But there's your proof. I'm not going to make you prove it at all. I just wanted you to see the proof before you use it. Let's use this proof, okay? So here's our first problem. We want to calculate the derivative. Now again, you can memorize this definition that we have over here, or the product rule. That's exactly what it is. But what I want you to think about is first times the derivative of the second, plus the second times the derivative of the first. That's really what we're doing here. So here we go. By the way, what's the first and the second? So this guy right here is the first, and this is the second. You see how that's a product, right? So we have h primed of x is equal to, now the first, we just recopy, 5x squared minus 2x times the derivative of the second. So what is the derivative of 3x plus 1? Okay, well the derivative of 3x we know is 3, and the derivative of 1 is 0. Don't feel like you have to write that 0, you don't. So this is, again, reminder, that's first times the derivative of the second. I'm just putting that little slash there to represent derivative. Plus, and now we write the second, 3x plus 1, times the derivative of the first. So what's the derivative of 5x squared minus 2x? Well, let's take a look at 5x squared first. Use the power rule and the constant multiple rule. So 2 times 5 is 10x minus the derivative of 2x is just 2, or 2 times 1, if that helps you feel better. Then your goal is to simplify your answer as much as possible. So that's going to be 5x squared minus 2x times 3 plus, and then over here we have 3x plus 1 times 10x minus 2. Now that's not an unacceptable answer, but it sure can be simplified a lot. Now when you simplify these big derivatives that we're going to run into, you do want to look for greatest common factors that you can factor out of this set and this set. They don't have any greatest common factors, so it's best to distribute. Like this 3, I'm going to distribute inside. That's going to give me 15x squared minus 6x. Here I am going to distribute and FOIL. 3x times 10x is 30x squared. 3x times negative 2 is minus 6x. 1 times 10x is 10x. And 1 times negative 2 is negative 2. When I add like terms, I have 15x squared. Ooh, actually I don't. Got a little carried away. 15x squared plus 30x squared is 45x squared. Negative 6x minus 6x is negative 12x, plus 10x is negative 2x, and then finally I've got minus 2. So that is completely simplified. Now I do want to show you this problem again though. I want to revisit it because, y'all, we could do this again where we just multiply this out at the beginning. Let me see if I can sneak it on this page. I know it's going to get a little congested, but let's don't use the product rule. Let's just FOIL this out. So my original function, 5x squared times 3x, is 15x to the third, right? 5x squared times 1 is plus 5x squared. Negative 2x times 3x is negative 6x squared. And negative 2x times 1 is negative 2x. When I combine like terms, that gives me 15x to the third minus x squared minus 2x. Now that's not my derivative, right? That's my original function. That's h of x. Now let's just use what we learned in the last section about the constant multiple rule, the power rule, or taking derivatives of polynomials. So when I take the derivative of 15x to the third, remember I multiply the 3 in the front. It gives me 45x. I reduce that exponent by 1, so squared. Second term, negative x squared, I multiply the 2 in front, so that would be minus 2x. I reduce that power by 1, so that's to the first. And then the derivative of negative 2x, the derivative of the constant multiple, you just jump inside. The derivative of x is 1, so that's minus 2 times 1, also known as 45x squared minus 2x minus 2. Now, it just happens to be that this problem was easier the green way if we multiplied it out first, but I needed to show you how to use the product rule, and I picked the simplest problem I could right off the bat as an example of the product rule. Okay, so let's try another problem using the product rule. If you'll notice, this one is not like the last one. The last problem we had 2 different ways we could handle that one. This is not one of those. We have no way to simplify this where we can use, our power rules. We just have to look at this as a product. And then you might start thinking, what is the product? It looks like 3 things multiplied together. Please don't say 4. Remember, sine of x is a team right here. So that's not sine times x. That's the sine of x. So when I think about a product, I'm thinking 5x to the third is my first. And hey, that's Buford. Y'all hear Buford? Sine of x is my second. And so the derivative, keep the first constant times the derivative of the second. Remember, first times the derivative of the second plus the second times the derivative of the first. So here we go. Y prime, proper notation, first times the derivative of the second. The derivative of sine of x is cosine of x, remember? And then plus the second, which is sine of x, times the derivative of the first. So what is the derivative of 5x to the third? So remember, we're using the power rule. Move the 3 in front times that 5. That's going to be 15. And then x, reduce that exponent by 1 squared. Now, you should get in the habit of looking to see if you can't simplify this. Remember the last problem? I said look for a greatest common factor. We do have a greatest common factor here. So y primed equals, notice both terms have a 5 as a common factor and an x squared. So I'm going to pull out a 5x squared times, okay? Now if I pull out a 5x squared, that leaves me with x times the cosine of x for my first term plus, And then notice there's a 3 left down here. It's better written in front of the trig function, so 3 times the sine of x next. And this is what I would consider completely simplified. I wouldn't mark it wrong up above, like for example, if you put y primed is equal to 5, that's not a 5. Let me try that again. A 5x to the third cosine of x plus 15x squared sine of x. That really is appropriate as an answer, but when we're going to use these derivatives for something else, and you know what's coming, we're going to use them to find certain values, it needs to be simplified like this. It's really going to make it easier, okay? Imagine setting that equal to 0. You need it factored and not like we have it down below. All right, so let's check out another problem here. Problem C, find the derivative. We've got y is equal to 3x times the sine of x plus 5 cosine of x. So what I want you to notice here is you've got 2 separate terms. You could think about these as 2 separate functions. If you'll remember from the last section that we covered, we have a sum difference rule. You're allowed to take the derivative of 3x sine of x separate than the derivative of 5 cosine of x and just add them together. So I'm thinking about this as 2 separate problems for the moment. But now look at your first term. Your first term has a product. So I'm going to say 3x is the first, while sine of x is the second function. And then 5 cosine of x I'm going to look at completely separate. Okay, so here we go. I've got y primed equals, so now I'm just focused on, remember, first times the derivative of the second. So I'm rewriting the first. That's 3x times the derivative of sine of x. Remember, that's cosine of x. So that's first times the derivative of the second, plus, and now I write the second, which is sine of x, times the derivative of the first. And the derivative of 3x, remember, 3 is a constant multiple, and the derivative of x is 1. So this is, again, second times the derivative of the first. Plus, now I'm focused on this 5 cosine of x business. The 5 is a constant multiple, so it just comes down. And the derivative of cosine of x, we know is negative sine of x. That's just a memorizer, right? We proved it, but now we can just memorize it. Now it's all about simplifying. So I'm going to clean it up a little bit. So I've got 3x cosine of x. I can just write that all together without parentheses. Sine of x times 3 is better written with the constant multiple in front, 3 sine of x. And then 5 times negative sine of x is negative 5 sine of x. And at this point, you should look for a greatest common factor, or even in this case, we have like terms. Look at here. I can combine those together. So I get y primed is equal to 3x cosine of x. And then positive 3 subtract 5 is going to give me minus 2 of these sine of x, guys. And again, no greatest common factor, so I'm going to leave that as is, and there's your derivative. Okay? Remember, what's the derivative for? The slope of the tangent line. So for any x value that you plug into this function, we would find the slope of the tangent line of this original curve at that point. But it didn't ask for that, it just said the derivative, which is just a function. Take a look at this character right here. It says the product rule may be extended to more than 2 factors. So if we need to take the derivative of, look, we've got 3 functions multiplied together here. We've got an f of x, we've got a g of x, and we've got an h of x. So what if you did have a function that had 3 factors multiplied together? Well, it's just an extension of our original product rule. What we're going to do is we'll take the derivative of the first one in line and hold the other 2 constant. That's the first term. Then we're going to take the derivative of the second guy in line, the g of x, and then hold the first and the last constant. And then finally, we're going to take the derivative of h of x down here and hold the first 2 constant. Remember, the order you multiply in doesn't matter, so it doesn't matter if the f prime of x is first or last written in that group, or if the g of x is in the middle. They're just keeping it in the same order. And remember, the first one, the first derivative, the second term, the second derivative, and the third term, the third derivative. Now, a lot of functions can be simplified so that you would not have to use this, but I could make one up where you would need to use this product rule where you have 3. I don't have an example for you here, but I bet one shows up in the homework. All right, you ready for a new rule? We've got theorem 2.8. It's called the quotient rule because you're dealing with a quotient. Y'all, that is Buford. That is my tree and walker coonhound that's just pitching a fit because my family's outside. Anyway, hush Buf. So we have the quotient rule. So we're taking the derivative of f of x divided by g of x. So look at what this mess is. It's g of x times the derivative of the top f of x minus f of x times the derivative of the denominator g of x over g of x squared. Now, how are you going to remember that? I often say the bottom, which is g of x, times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. I say that a lot. That's just what's going on in my head. There's also this cute little trick called low d high minus high d low over low squared. Okay, so what does that mean? Low is your bottom. Low d high means the derivative of the top one, the high one, minus high, which is the top one, d low times the derivative of the bottom over low squared. So low d high minus high d low. And then you just got to remember it's over the denominator squared. When you do enough of these, and you must, to practice and get good at this, you must do enough of these. One of these things will stick in your head, I promise. We got to do a proof, though. Not allowed to use it until we do a proof. So here's a proof. Let's get started. You know how we're going to start? We're going to use the definition of the derivative. So what is that? F of x plus delta x minus f of x over delta x. And we're going to take the limit as that goes to 0. Well, as delta x goes to 0. When I plug that in, then remember I'm plugging x plus delta x in everywhere there's an x. So that's why I have the first fraction. Then minus the original function, which is f of x over g of x, all divided by delta x. Now we got to simplify this mess. What would you do to simplify this? You probably would handle this complex fraction, right? You'd find a common denominator and combine this up here in the top. Well, that's what I did too. So watch this. Next, find a common denominator, and I'm going to find more space because it's certainly not happening on this page. So let's move everything up. There we go. Now look, here's our common denominator. I multiplied, see, here's where we are. I multiplied this first function by g of x over g of x right there. I'm going to highlight it for you. So this is the new stuff. I multiplied by g of x over g of x there. And over here, I multiplied by g of x plus delta x over g of x plus delta x because that was my original denominators. Combine that together. Write just one denominator instead of these two separate guys and just rewrite what I have in the numerator there. So now what do? Well, we invoke a trick, right? All the best proofs have some crazy trick. So here's our trick. We're going to subtract and add. This time I did it for you in red so you could see a little bit better. F of x, g of x. Why? Because it works, but you'll see what I mean. But that's just equal to 0, right? So we're totally allowed to do that, no problem. Now, what do you think I should do next? Maybe we should try to split this up? Or wait a minute, I still have a complex fraction, don't I? Do we need to do something with that? Let's see. So, it says now factor the greatest common factor of the first two terms in the numerator and the last two terms in the denominator. So see, I left it as a complex fraction. We'll deal with that later. But I factored out my first two terms here. Okay, I factored out that common g of x. I'm going to highlight that for you so you're real clear on this. So there's g of x. I factored that out front. It's in green. In the second two terms, I factored out a common. What do we have in common there? See that f of x? And there it is in green, factored out. All right, and there's that line again, just in case you missed it. Now we need to invert and multiply. See, I wanted to do that earlier, but we're doing it now, which is perfectly fine. Now, when I flipped it, notice I just put it under the numerator there. Can I do that? Does that make sense? Turns out it does, because if we flip again, we would get what we need. So it's just kind of a way of reorganizing this thing, but you are allowed to do this, okay? Now next, It's going to split this mess up by using the sum different rules of limits and the quotient rule of limits. Okay, so we're going to write this, the sum difference rule of limits. You can just split this up into two separate limits if you want to. And then the quotient rule, we're going to take the limit of the numerator, the big numerator, and the denominator separately. So watch this written out. Here it is. So notice how I split up the numerator. The minus that's here is in between these two limits. And then I also, to save space, I did two things in one step. I split the limit up of, I'm going to highlight all this up top, this as a separate limit than this. You see? Are we allowed to do that? Sure we are. Limits you can split up: addition, subtraction, multiplication, and division. The main thing is the limits have to exist, so we have to focus on that as we go through this process. What's the next step? It says, finally, to wrap up this proof, let's use the product rule for limits to split up the two products in the numerator and the product in the denominator. Okay, so watch. What is the, we'll do this in red, what is the limit as delta x goes to 0 of g of x? Well, that's just a constant. There is no delta x in g of x, so that is just g of x. That's what I have right here. Okay, so next, the second limit. So I'm taking this limit right here. Again, that's the product rule I talked about splitting up. What is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x? Well, you recognize that. That's the definition of a derivative, right? So that's this f of x, f prime of x that I have here. Okay? And then, once again, I'm doing the same thing. I'm looking at this limit right here. Since there is no delta x in f of x, that's just f of x. When you take that limit, it's a constant. And then when I take the limit of the one next to it, the g of x plus delta x minus g of x over delta x, that's g prime of x. Now let's look at the denominator. Okay? I'm splitting that up as two separate limits as well. The limit as delta x goes to 0 of g of x is just this first g of x. Now here's where it gets fun. The limit as delta x goes to 0 of g of x plus delta x is also g of x. Now the reason that happened is because I substituted in 0 right here for delta x. The reason I'm allowed to do that, if you'll remember, is because we know g of x is differentiable, which means it's continuous. And since it's continuous, I'm allowed to just substitute 0 in to delta x. Now, since I have a g of x times g of x, I have g of x squared. Now, a lot of you are thinking, I do not care, just tell me how to use it. But I want you to realize this does come from the definition of the derivative. And now that we know that it does, we can use this rule or theorem to make finding the derivative so much easier than using that big old definition. Okay, here we go. You ready to use this thing? So it says find f prime of x, in other words, find the derivative. Then it wants us to find f prime of c. But that's secondary. Let's just find f prime of x right now. We will worry about the c stuff later. So f prime of x, I must use the quotient rule. Why? Because I have a quotient. I have a fraction right here. And if you find that you have variables in the numerator and the denominator, that's telling you you need to use the quotient rule. Okay? So either way you want, bottom times the root of the top, minus the top times the root of the bottom squared, or low d high, minus high d low. I think you might like it that way, right? Low d high. So low, which is x plus 4, d high means the derivative of the numerator. So what is the derivative of x minus 4? It's 1, right? It's really 1 minus 0, which is 1. So that's low d high minus high, which is x minus 4. And then d low is the derivative of the denominator. What's the derivative of x plus 4? Well, the derivative of x is 1, right? The derivative of 4 is 0. And I probably should have wrote 1 plus 0 when I did it here as well. Or 1 minus 0 in that case. Divided by, don't forget the denominator, and it's the denominator squared. So this is going to be x plus 4 squared. then y'all, it's all about simplifying. So f prime of x is equal to, now this is just 1, so x plus 4 times 1 is x plus 4, minus, okay, now that's 1 also, so I would distribute that if it weren't just 1. But hey, you got to distribute this minus right here. Okay, the product rule had a plus in it, so less chance for error. But this quotient rule's got a minus, so this is going to be minus x, and then plus 4 over this x plus 4 squared. I continue to simplify. F prime of x is equal to, now I got an x and a minus x. Hey, that was nice. 4 plus 4 is 8 over x plus 4 squared. And that's my derivative. That's a perfect way to write it. Don't feel like you have to do anything else to that. Now it asks us to find f prime of c. That's no problem. All we had to do is plug 3 in for my x value in the derivative. So f prime of 3 is equal to 8 over 3 plus 4 squared, which is 8 over 7 squared, which is 8 over 49. Make sure your fractions are lowest terms, and that is. Now, what did we just find? What is this 8 over 49? It is the slope of the tangent line at x equals 3. So if we were to graph this curve, I'm not going to right now, but if we were to graph this curve and plot the point 3, whatever we get when we plug 3 in for the y, and look at the slope of that tangent line is 8 over 49. Okay, example E. This is an interesting problem for you. It says find the equation of the tangent line. You have to reflect back what's going on here. First of all, to find the equation of the tangent line, you need a slope. To find the slope, you need a derivative. So, by the way, everything in this chapter starts with step 1, find the derivative. That's not 100%, but it probably is 100%. You know what I mean? So, find the derivative first. Then, we can plug in our x value, which corresponds to the c value on the previous problem, to find the slope. And then finally, we write it in terms of y equals mx plus b. But one step at a time, let's find the derivative. Now, how about this derivative? What's going on here? It looks like a product because we're multiplying x squared times what's in parentheses here. Then inside there, we have quotients. Now, here's what I suggest. You want to write your function in the simplest form you can before you take the derivative, or in the easiest form to take the derivative, and that takes experience, I know, but y'all distribute that x squared inside. It'd be so much easier to work with. So I have g of x. This is not g prime of x. I'm not taking the derivative yet. X squared times 2 over x will be 2x squared over x, which requires some simplifying, right? Minus x squared times 1 over x plus 1 is going to be minus x squared over x plus 1. If I continue to simplify, that's going to be g of x is equal to, these x squareds cancel, that's just 2x minus x squared over x plus 1. Now, that to me is what would be easier to take the derivative of, not that original function. And when you take this derivative, think about these as two separate terms. This second guy, I do need to use the quotient rule. The first guy, just 2x, hey, that's just plain old power rule times constant multiple rule. We got that, just a separate term. So here we go, g primed of x, the derivative of 2x, remember the 2 is a constant multiple, I rewrite it, the derivative of x is 1. If you just wrote 2 there without the 2 times 1, that's perfectly fine. Minus. Now here we go with this low-d high minus high-d low business, right? So low is x plus 1. D high, derivative of x squared is 2x. Minus high, which is x squared. D low, what's the derivative of x plus 1? 1 plus 0, which is just 1. Over, do not forget the denominator, x plus 1 squared, or low squared. Now we need to simplify this to make it look a little better. Now remember, our ultimate goal is just to plug a number in. So you got to question how much you really want to simplify. If you're just going to be plugging in x is equal to 1, but I'm going to make it look a little better, okay? So this is going to be 2x times x plus 1 minus x squared over x plus 1 squared. Now, if I were just asked to find the derivative, I would simplify this more. Distribute the 2x inside, add like terms, simplify, maybe even find a common denominator and write this as one fraction. But y'all, I'm supposed to just substitute this 1 in to my problem. So instead, I'm just going to do that now so I don't accidentally make some silly mistake and then get it wrong. Let's go ahead and plug the 1 in, and I'll do that in blue. So g primed of 1 is going to be 2 minus 2 times 1 times 1 plus 1 minus 1 squared, all divided by 1 plus 1 squared. Now remember, while we're doing this, we're trying to find the slope of the tangent line. So this is 2 minus, now when I multiply and subtract all this, this is 2 times 1 times 2, which is 4. 4 minus 1 is 3. 1 plus 1 is 2 squared is 4. So now we have 2 minus 3/4. Need a common denominator, so that's g primed of 1. That would be, what, 8/4 minus 3/4, which gives me 5/4. So my m, or my slope of the tangent line, is 5/4. Now I'm going to go with one more color because now we're working with y equals mx plus b. It didn't want to just know the slope of the tangent line, it wanted to know the equation of the tangent line. So I have y. What's y? Well, that is the y value when I plug in x equals 1. It was given. It's 3/2. So I have 3/2 is equal to 5/4. My x is 1 plus b. Now I'm solving for b. So this is 3/2 minus 5/4 is equal to b. Now I need a common denominator. So that's 2 over 2, and that's going to give me 6/4 minus 5/4, which is 1/4 is my b value. Finally, I got a b. So final answer, let's do this in black. Final answer is y is equal to, my m, remember, is my slope, 5/4 x, and my b is 1/4, so plus 1/4. Does that look good? Again, step by step. Take the derivative. Then plug in your x value into the derivative. That finds the slope of the tangent line, which is 5/4. Then work with y equals mx plus b. And so your y is going to be whatever your y value, either it's given or you have to find it. Sometimes you have to take the 1 and plug it into the original function to find y. And then your 5/4 times your x to find b. And then finally, leave y and x in your equation and plug in your m and your b, and you're finished. I'm going to wrap this video up now because it's getting a little long-winded. I'm going to come back again, and we're going to do some more tidbits. Oh, let me do one more page. Just hang with me. One more page. Check this out. And then we'll come back and prove another theorem and work with higher order derivatives. But I want to show you this before you go, because this says when using the quotient rule, please use the constant multiple rule when applicable. In other words, don't use the quotient rule when there's an easier way to do it, please, because it'll make your life miserable. This one is not screaming quotient rule. You know what you want to do with this one? You want to rewrite it, and that's always what I say, rewrite. So rewrite this as 1/3 x to the 5th plus 4/3 x to the 3rd. You see that? I just put the 3 underneath each one of these guys separately. That way when you take the derivative, y primed, multiply the 5 in front, so that's 5/3 x, reduce that power by 1 to the 4th. And over here, move the 3 in front. Now when you multiply 3 times 4/3, you see that those 3's cancel, right? That just gives you 4x, reduce that by 1, squared. If you didn't catch that, just pause it and do it yourself, and you'll see where that came from. Y'all, that's so much easier than doing low d high minus high d low over low squared. This is not a quotient either, okay? If there's not a variable in the denominator, please don't use the quotient rule. It's just too much trouble. Now, it would work, by the way. It's just way too much trouble. So this, just think about it as y is equal to 3/7 x squared. So when I take the derivative, y primed, That's equal to, I'm going to multiply the 2 in front. So that's 2 over 1, right? So 2 times 3 is 6/7 x, and now that's to the first power, and that's better written as just 6/7 x, or 6x over 7. That's right also. Now this third guy, he could stand for some simplifying. So the first thing I think I would do is distribute the 5 inside. That's not required, but it'd make me feel a little better. So 5 times 4x is 20x minus 5x squared over 2x squared. Now don't stop there, because you could put that 2x squared underneath each one. That's 20x over 2x squared minus 5x squared over 2x squared. Buford. And that equals, hold on. Okay, I'm sorry about my dog. He's angry and he won't be quiet. But 20x over 2x squared. The 20 and the 2 cancel. That gives me 10. Now, that would be over x. You agree I should write that as 10x to the negative 1? We talked about that in the last video, right? And then minus, these x squareds just cancel 5/2. Now, I haven't even done any calculus to it yet. Now, I'm ready to take the derivative. So y primed equals, now, power rule, right? I multiply the negative 1 in front. That's going to be negative 10x. And I reduce that by 1. That's to the negative 2. And then the derivative of 5/2 is 0. Now, I could rewrite this as y prime is equal to negative 10 over x squared. And then we're done with that one. So it's really a lot of algebra before we finally took the derivative. Now, again, you can use the quotient rule on this if you want to, but I try to not use the quotient rule. I mean, if you can avoid it, and it'll be a lot easier. Let's do one more of these before I wrap up this video. Now, this guy kind of corresponds to what we did here. Do you want to use the quotient rule, low d high minus high d low? You can. You would get it right. But what I can do is just rewrite this as 5/3 times x to the negative 2 power. That would be easier, right? And so when I simplify this thing, actually when I take the derivative, I've already simplified it. I move, remember, multiply that in front. Now that's like multiplying by negative 2 over 1. So 5 times negative 2 is negative 10/3, and that's going to be x, and then reduce that by 1, it's going to be negative 3. Now, if I wanted to rewrite it, I could write that as negative 10 over, the 3 is still in the denominator, and this x to the negative 3 moves to the denominator, and there I am. Hope this helps. Make sure you get a lot of practice, and let me know where you're stuck.